Testing. Can you hear me? Hello. Can everyone hear me? So I took a break from calculus streams, but now I'm trying to come back to it. Last stream was in my last calculus stream was on June 17th. It's July 24. So it's been more than a month. So last time I learned about yeah, differentiation of functions of several variables. Last thing I learned about Lagrange multipliers. It was like an optimization method where there's an optimization function. There's like this optimization function. They're showing the level curves of different values. And you want to find a gradient of this function which matches the gradient of another function. So the gradient of this is a multiple of gradient of another function. So basically the gradient vectors are both parallel. That was it's an optimization method, and that was the Lagrange multipliers. And that's the last thing I learned. This stream, I'm going to start multiple integrals. So yeah, I will try to read these three chapters and do some of the exercises. That's my plan for now. In this chapter, we extend the concept of a definite integral of a single variable to double and triple integrals of functions of two and three variables, respectively. We examine applications involving integration to compute volumes, masses, and centroids of more general regions. We will also see how the use of other coordinate systems such as polar, cylindrical, and spherical coordinates makes it simpler to compute multiple integrals over some type of regions and functions. So, volumes and double integrals. We begin by considering the space above the rectangular region R. Consider a continuous function f of x, y is more than or equal to 0 of two variables defined on a closed rectangle R. Okay, so we have this region. Sorry, we have this surface and we have this region. Here, AB times CD denotes the Cartesian product of two closed intervals AB and CD. So AB is on X and CD is on Y. It consists of rectangular pairs such as X is between A and B and Y is between C and D. The graph of F represents a surface above the XY plane with equation C is equal to F of XY. Let S be the solid that lies above R and under the graph of F. The base of the solid is a rectangle R in the XY plane. We want to find the volume V of the solid S. We divide the region R into small rectangles Rij, each with area delta A and with sides delta X and delta Y. We do this by dividing the interval AB into M subintervals and dividing the interval into N subintervals. Hence, X is B minus A divided by M, delta Y is D minus C divided by N. And then delta A is delta x over delta x times delta y. So this area of the small rectangles is delta A. So what are these points? This over here. Okay, this is delta x, this is delta y, this is r I j. So it starts with 0, right? So the first column and the first row at the bottom is both 0. This is rij. This point is xi, yi. This is a point in xij and yi between. Hold on. What is this notation? The volume of the thin rectangular box above Rij is f of xij yij delta A, where the star is arbitrary sample point in each Rij as shown in the following figure. Okay, so this over here is an arbitrary point within the subregion. So we have 0, 0, wait, we have 1. Hold on. So this here is 1. If this is 1, then this entire region is x star 1. This is 2. This entire region is x star 2. So the first column is 1. The first row is 1. So 1, 2, and then 1, 2, 3. Right. So I is 2 and then j is 3. Okay. So we are approximating this by the volume of a rectangular prism. We are doing this by f of x. Okay, f of x I star I j star y I j star. So the area of this region times it by the height. And this here is some sample point within the region. Using the same idea for all subrectangles, we obtain an approximate value of the solid S as this. This is known as a double Riemann sum. Can be used to approximate the value of the volume of the solid. Here is the double sum means that for each subrectangle, we evaluate the function at the chosen point. Multiply by the area of each rectangle and then add all the results. As we have seen in the single variable case, we obtain a better approximation to the actual volume if m and n became larger. This goes to infinity. Okay, so delta x and delta y is going to 0. Note that some approaches a limit in either case, and the limit is the volume of the solid with base r. Now we are ready to define the double integral. The double integral of a function f of xy over the rectangular region r in the xy plane is defined as this. Double integral delta a. Okay. Do we have, is like r underneath path of the notation? If f of x, y is more than equal to 0, then the volume V of the solid S, which lies above R in the xy plane under the graph of f, is the double integral of the function f of xy over the rectangle R. If the function is never negative, then the double integral can be considered a signed volume. in a manner similar to the way we define the net signed area in the definite integral. Because in some surfaces, this f value can be negative, so we can have negative area. Setting up a double integral and approximating it by double sums. Consider a function c is equal to 3x square minus y over a rectangular region 0 to and 0 to 0 to. Uh, okay. Set up a double integral for finding the value of the signed volume of the solid S that lies above R and under the graph of F. Divide R into four regions. Oh, this is an exercise. I don't like the repetition, but so I'm going to skip this one, but I do get the idea though. Now that we have developed the concept of double integral using a rectangular region R, this concept can be extended to any general region. However, when a region is not a rectangle, the subrectangles may not all fit perfectly into R. Particularly if the base area is curved, we examine this situation in more detail in the next section. Where we study regions that are not always rectangular and subregions may not fit perfectly in the region R. Also, the heights may not be exact if the surface C is equal to f of xy is curved. However, the errors on the side and the height where the pieces may not fit perfectly within the solid S approaches 0 as m and approach infinity. Since delta A is equal to delta x times delta y, we can express dA as dx dy or dy dx. So this can be written as integral dx dy or dy dx. Some properties, the sum is integrable and you have this. If c is a constant, then c is integrable and we can take the c out. If r is S union t and S intersecting t is null, except an overlap on the boundaries, then we have this the region S plus the region T. If f of xy is more than or equal to g of xy for xy in R, then the integral is also higher. If we have M, the area is oh, it's M times the area of the region. Right. So f of xy is between small m and big M, then if we multiply, if they, then their volume is also in between, right? Then the volume of f of xy is also in between the volume with small m and volume with capital M. In this case, where f of xy can be factored as a product of g of x only and a function of h of y only, then over the region, the double integral can be written as this f of xy, and then we have integral of this and integral of this. So far, we have seen how to set up a double integral and how to obtain an approximate value for it. We can also imagine that evaluating double integrals by using the definition can be a very lengthy process if we choose larger values for m and n. Therefore, we need a practical and convenient technique for computing double integrals. In other words, we need to learn how to compute double integrals without employing the definition that uses limits and double sums. Basic idea is that the evaluation becomes easier if we break a double integral into single integrals by integrating first with respect to one variable and then with respect to the other. The key tool we need is called an iterated integral. So assume a, b, c, and d are real numbers. We define an iterated integral for a function f of xy over the rectangular region R as a to b and c to d. Right, so we are integrating with respect to y, and then we are integrating with respect to x. And then we can also flip them, integrate with respect to x first, and then integrate with respect to y. So this notation means that we integrate f of xy with respect to y while holding x constant. Similarly, the notation means that we integrate f of xy with respect to x while holding y constant. The fact that double integrals can be split into iterated integrals is expressed in Fubini's theorem. Think of this theorem as an essential tool for evaluating double integrals. Suppose that f of xy is a function of two variables that is continuous over a rectangular region. Then we see from figure 5.7 that the double integral of f uh, over the region equals an iterated integral. More generally, Fubini's theorem is true if f is bounded on R and f is discontinuous only on a finite number of continuous curves. In other words, f is integrable over R. Right. Use Fubini's theorem to compute the double integral where f of xy is equal to x. And we have this region. Example 5.2. So we have R, f of xy, dA, and we have f of xy is just x. So the graph, if you slice the parallel to the x-axis, it will look like this, but in 3D it will look like, how should I draw this? Like this. Like it's coming diagonally. Let me see if my guess was right. Xy is equal to x. Yeah. Now, if we want to integrate this, derivate with respect to x and then derivate with respect to y. And then we have this is just x. Do we add a plus c because it's the signs are not given? And then we have with respect to y, which is just x squared y over 2 plus t. Because it's plus another constant, like let's say c1, and then from this integral we get c2, and then we add them to get d. So x squared y, does that make sense? So the area of a triangle, could be x times y divided by 2. Then we are extending it like this, right? So that's why this times x. So that makes sense. And this is over a region 0, 2 and 0, 1. So it's not indefinite. So 0, 2 in the x and 0, 1 in the y. We have x square over 2, 0, 2. We have 2 over here. 2 square 4 divided by 2 is 2 minus 0. We have like this. And then we have 2y, 0 and 1, which would just give 2. Evaluate the double integral where r is in this region. So dA, what properties did this say? 1 and 2. Sum and constant property. So we have example 5.3. Xy minus 3xy square. 0, 2 and 1, 2. So the first property is say 0, 2, 1, 2. And then we can take the constant out. So treating y as constant, we are left with x square or 0, 2. Square over 2. And then we have we plug into, if we plug in 0, it will, all of this will be 0. If we plug into 4 over 2, we have 2y. 4 over 2 again, but this time 2y square. Two and 1. Now we integrate this. 2y square over 2. You're left with y square. You have 2 over 3 y cubed. 2 and 1. But the thing is, the 3 will cancel out. So 4 minus 1 is 3. And then over here, 2 cubed is 8. 2 cubed is 8. Minus 1, 7. 3 minus 14. Minus 11. Uh, okay, let me just read this example. Switching the order of integration. Consider the double integral over the region. Express the double integral in two different ways. Analyze whether evaluating the double integral in one way is easier than the other and why. Evaluate the integral. If we integrate with respect to y first and then integrate with respect to x, we see that substituting y is equal to f of x, which gives du is equal to x dy. As the inner integral is simply this. We can change the limits to be the function of x. When integrating with respect to x first and then integrating with respect to y requires integration by parts for the inner integral. You have u as x and dv is equal to sine xy dx. Since the evaluation is getting complicated, we will only do the computation that is easier to do, which is clearly the first method. Double integrals are very useful for finding the area of a region bounded by curves or functions. We describe this situation in more detail in the next section. However, if the region is a rectangular shape, we can find its area by integrating the constant function over the region. Find the volume V of a solid S that is bounded by the elliptic paralleloid, the planes x is equal to 3 and y is equal to 3, and the three coordinate planes. The volume of the solid S that is bounded by the elliptic paraboloid, paraboloid, 2x square plus y square, 2x square plus y square is equal to 27, 2x square plus y square plus c. Let's do y is equal to 3 and x is equal to 3. I don't get what they want me to. Okay, so this region x is equal to 3, y is equal to 3, bounded by the elliptic paraboloid, and the planes x is equal to 3 and y is equal to 3, and the three coordinate planes. So what's the region R here? R is negative 3, 3 and negative 3, 3. Hold on. C is more than equal to 0. It's not clear to me what they want. Figure 5.9a. Why did they choose 3 and minus 3? First, notice that the surface C, figure 5.9a, So the surface above the square region minus 3, 3 and minus 3, 3. The solid S lies under the surface region above the square region 0, 3, 0, 3. Find the volume of the solid S. It is bounded by the elliptic paraboloid. The planes x is equal to 3 and y is equal to 3 and the three coordinate planes. I think by coordinate planes they mean the xy plane, the xz plane, and the yz plane. So they mean so z is more than 0, x is more than equal to 0, and then y is more than equal to 0. And between 3, between 3. And let's change c from 0 to 30. Yeah, so I think what they want is negative 3, sorry, between 3 and 0 on both the x and y. So this is the square region and this is the upper part. This is the volume they want us to find. Never mind. Okay. So if that's the case, example 5.9, we have between 0 to 3, 0 to 3. Z, X region, Y region. So 27 minus y square minus 2x square dx dy. 27 minus y square minus 2x square dx dy. Now we can separate them. Minus it with minus 2 we have 0 3 27x, right, minus it with 0 3 x y square 3 0. Then we have x cube over 3. We have, what's 27 times 3? 81. We have 81 3 and 0. I can take the 3 outside. Can take the 3 outside here as well. 3 cubed minus 0. 3 cubed minus 0. 3 times 3, 9. And one of the 3 gets cancelled. So I just left with 9. Now we have 81y03. We have y cubed over 3, but the thing is it cancels out with this 3. So we are just left with y cubed. Minus it with 2, 9y. But I can just multiply it with 18. So it's 81 times 3. 243. And the 0 gets useless. 8 times 3 is 9. Times 3, 27. Minus it with, it's 18 times 3. 54. This is 243 minus 84 minus 27 minus 54. 162. Let's see. That sounds about right. Yeah, it is. Similarly, we can define the average value of a function of two variables over a region R. The main difference is that we divide by area instead of the width of an interval. Yeah, so this over here is the average value of a function of two variables. So the volume divided by the region. Double integrals over general regions. An example of a general bounded region D on a plane is shown in figure 5.12. Since D is bounded on a plane, there must exist a rectangular region R on the same plane that encloses the region D. That is, a rectangular region R exists such that D is a subset of R. Okay, so previously we did a rectangular region. Now we are doing a region D within R. Since Z is defined on a general planar bounded region D as in figure 5.12, in order to develop double integrals of f over d, we extend the definition of a function to include all points on a rectangular region R. and then use the concepts and tools of the preceding section. But how do we extend the definition of f to include all points on R? We do this by defining a new function g on R as follows. So the new function g is equal to f if so within D, g of x is equal to f of x, but outside it's 0. Now we might have some technical difficulties if the boundaries of T is complicated. So we assume the boundary is a piecewise smooth, continuous, simple closed curve. Also, since all the results developed in double integrals over the rectangular region used in integrable function, we must be careful about g and verify that g is an integrable function over the rectangular region R. A region D in the xy plane is of type 1. If it lies between two vertical lines on the graph of two continuous functions, g1 and g2. That is, t is equal to xy, where x is between a, b, y is between g1x and g2x. Okay, so we are defining the upper and lower boundaries by a function. And these functions can connect even at both points. Region D in the xy plane is of type 2 if it lies between two horizontal lines. The graph of two continuous functions, h1y and h2y. Okay, so the y values are straight. So the y cutoff point is straight, but the x cutoff point is defined by a function of y. Consider the region in the first quadrant between functions y is equal to root x and y is equal to x cubed. Describe the region first as type 1 and then as type 2. So type 1 would be we have x. So we take the point where they intersect. Hold on. I was doing it in my head, but let me just, how do I cut? This is 5.11. So where do they intersect? So where does this happen? X to the power of 6. So this only happens when x is equal to 1, right? So we have so D is defined as x, y, where x is between 0 and 1. And Yeah, we can define g1 as root x, sorry, g2 as root x, so y has to be below root x. We can define g1 as x cubed, so y also has to be above x cubed. Okay, double integrals over non-rectangular. Wait, let me see the answer. Why is my laptop so slow? Double integrals over non-rectangular regions. Suppose Gxy is an extension to the rectangle R of the integrable function f of xy defined on the region D where D is inside R. Sample regions are shown in figure 5.12. Then g of xy is integrable and we define the double integral of f of xy over D by this. Fubini's theorem, strong form. For a function f of xy that is continuous on a region D of type 1, we have so type 1 region D. So we integrate with respect to y first and then with respect to x. Right. Similarly, for a function f of xy that is continuous on a region D of type 2, we have integrate over x first and then with respect then we integrate with respect to y. The integral in each of these expressions is an iterated integral similar to those we have seen before. Notice that in the inner integral of the first expression, we integrate f of xy with x being held constant, the limits of integration being g1 and g2x. Value the integral where d is shown in figure 5.16. 5.15, 5.17, 5.16. Wait, what? All right. Nina, you saw the answer. We can express region D as a type 1 region integrate from y. Okay, let's do this. So they said type 1 region, right? So it's defined similar to this. X is fixed and the boundaries of y is a function. Mm, so it's so with type 1 we have integrate with y first. So in what regions? Okay, D is shown. Construct here. So this is the region. 0 to 2. So D is all the xy where x is between 0 to 2 and y is above half x and below 1. So first we derivate with respect to y, and x square would be a constant. We have wait, if we derivate, like let's say e to the power of 2x, this is the same as derivating e to the power of x squared, and derivative of the outside with derivative with respect to e to the power of x will just give us 2 to the e to the power of x, and then we derivate the outside. So I'm using the chain rule here. Derivate the outside and then derivate the inside. We get this, right? Similarly, we have this to the power of y. We have wait, and then we divide. Then we, why do I feel like this is wrong? If we derivate this, wait. Put y inside, x outside. Y inside, x outside. So derivate e to the power of y. Derivate the outside first. You're left with x times e to the power of y. Let me just make sure I'm right about this. I don't know why I'm so confused. So treating x as a constant and using the chain rule, we have this times it with respect to e to the power of y, we get this, and then derivating e to the power of y with respect to y, it's just e to the power of y. And then we are left with therefore okay, I'm assuming this is correct. So uh, x over 2 is the lower one. You place x over 2 here. And then minus it with e to the power of y. X and x cancel, and we can take the 2 outside, but we will do that later. Y x over 2, and then divided by, there's no divide. Yeah, we'll just take the 2 outside, and then minus it with, sorry, this is with respect to x, and minus it with, now it's y over 2, which is the constant in this case. Oh no, wait, I made a mistake. I replaced x, I was supposed to replace y. This is all wrong. So x over 2 goes here. Minus it. E, now this is 1, x, x, dx. Now we have e to the power of x square over 2 minus it with e to the power of x. X square over 2 and then e to the power of x. Why is their sign flipped? Actually, yeah. I think I made a mistake again. This is plus, this is minus. You evaluate the higher one first and then the lower one. I don't know why I did the opposite. Now, what's the integration of this? Integrate with respect to x using u substitution. So let's say u is equal to x square over 2 du with respect to dx is x 2 0 e to the power of x dx and then minus it with 2 0, not 2 0, e to the power of u over here. X dx will become du. But then instead of, okay, 0 is fine. Instead of 2, 2 is also fine. 2 is fine. It's fine. Yeah, so e square minus e to the power of 0, which is 1, then minus it with e square minus 1. Is this correct? Oh, yeah. So this and this cancel out. Hold on. They got 2 over here. I'm getting 0. I mean, these two integration are the same, so that's why I may be getting 0. It's the previous integration. How did they get x? Yeah, this is x e to the power of x. Okay, so we got this. What about this? If I want to write it in terms of u, I got rid of x dx. What about, so x is equal to, no, um, okay, I need to find the integration of this. So derivate this with respect to root to u. We get this. I derivate root to u with respect to u. I think it's better if I write half. So half, then minus half. Why am I getting confused? Yeah, we'll look at this later. Decomposing regions into smaller regions. Suppose the region D can be expressed as D1 union D2, where D1 and D2 do not overlap except at their boundaries. Then we have this plus this. This theorem is particularly useful for non-rectangular regions because it allows us to split a region into a union regions of type 1 and type 2. Then we can compute the double integral on each piece in a convenient way as in the next example. Express the region D shown in figure 5.19 as a union of regions of type 1 or type 2 and evaluate the integral. So this region can be decomposed into a union of three regions of type 1 and type 2. So I'm guessing this quadrant is one region, this quadrant is one region, and this quadrant is another region. Let's see. I think I will do most of the exercise off stream. As we have seen already, as we have already seen, when we evaluate an integrated integral, sometimes one order of integration leads to a computation that is significantly simpler than the other order of integration. Sometimes the order of integration does not matter, but it is important to learn to recognize when a change in order will simplify our work. Reverse the order of integration in the iterated integral, then evaluate the new iterated integral. We saw reversing the order in the previous chapter, right? Evaluating an iterated integral by reversing the order of iteration. Consider the iterated integral where z is this over a triangular region R that has sides on x is equal to 0 and y is equal to 0 and the line x plus y is equal to 1. Sketch the region and evaluate the iterated integral by integrate integrating first with respect to y and then integrating first with respect to x. Should I do this? Because I already took a lot of time in the previous example. X is y, x is 0, x plus y is equal to 1. So it's like it's a plane, right? How do I sketch it? So it's like it's more like I don't know how to draw it. X plus y is equal to 1. It's 10 to 3D. How do you draw it in a 3D plane? So we have this region, and this triangular region. Right. Calculating volumes, areas, and average values. We can use double integral over general regions to compute volumes, areas, and average values. The method are the same as those in double integrals over rectangular regions, but without the restriction to a rectangular region. You can now solve a wider variety of problems. Find the volume of the solid bounded by the planes 0, 0, 0, and 2x plus 3y plus z is equal to 6. 2x plus 3y plus z is equal to 6. So we have this plane, and then we have 0, 0, 0. Example 5.17. We are integrating 2x plus 3y. No, z is equal to 6 minus 2x minus 3y. Let's do it with x first and then y. And we will make it a type 1 scenario where we'll put this 0. So we have this as 0, then 2x plus 3y is equal to 6. Then the region D is a set of all points where x is between 0 and and if y is 0, x is 3, right? X is between 0. How do I reset the origin? So it intersects at x is equal to 3. Yeah. So 0 and 3 and function of y. So y is above 0 and below 6 minus 2x over 3. 6 minus 2x divided by 3. So let's integrate over y first. We have 6 minus 2x minus 3y. So integrating them separately, we have 2xy minus 3x squared over. So 3 times 6 is 18. So 6 divided by 3 is 2. 2 times 6 is 18. 2 times 2 is 4. Is this right? Imagine if they have a simpler method. Let me see if I'm actually right. I don't think I'll complete the entire thing. I just want to know if I'm heading in the right track. So we have this region. We have this. Integrate this, we get this. And then, oh yeah, I was heading in the right region. But simplifying this is the issue. How did they simplify it like this? Also, this entire thing is square. So 18 minus 4x minus, let's write 2. So minus 4x minus 4 over 3x squared minus 3 over 2. Am I heading in the right direction? Is there some simpler way to do this which I don't know about? Minus, we have 2 times 2 is 4 minus 4 over 3x, but that appears twice, so 8 over 3x minus 4 over 9x squared. Uh, 4 times 3 is 12, 6 minus minus becomes plus. E3 cancel, we have 4x minus minus becomes plus again. And then 2 over 3 x squared dx. So we have 12. This minus this is 12. Minus 18 plus 4 is minus 14x minus and plus. We are left with minus 2 dx. And I don't think this is correct. They took 2 over 3 out. Two, 3, 0, 6, 7 x square over 3. How do you take the 3 out though? Is it like is it like this? When you put the 3 back in, you get 6. They got x minus 3. I got nowhere close to that. Um, yeah, we'll think about this later. 2 liter. And then this one. Improper double integral. An improper double integral is an integral where either t is an unbounded region or f is an unbounded function. For example, this is above or equal to 2 is an unbounded region and the function over the ellipse is an unbounded function. Hence, both of the following integrals are improper integrals. In this section, we would like to deal with improper integrals of functions over rectangles or simple regions such as f has only finitely many discontinuities. Not only such proper integrals can be not all such improper integrals can be evaluated. However, a form of Fubini's theorem does apply to some type of improper integrals. If D is a bounded rectangle or a simple region in the plane defined by this, and also by this, and f is a non-negative function on D with finitely many discontinuities in the interior of F, then we have this from A to B, from this function to this function. We can flip the x and y. It is very important to know that we are required that the function be non-negative on D for the theorem to work. We consider only the case where the function has finitely many discontinuities inside D. In some situations and probability theory, we can gain insight into a problem when we are able to use double integrals over general regions. Before we go over an example with double integrals, we need to set up few definitions and become familiar with some important properties. Consider a pair of continuous random variables x and y, such as birthdays of two people or the number of sunny and rainy days in a month. The joint density function f of x and y satisfies the Probability that x and y lies in a certain group T. Since the probabilities can never be negative and must lie between 0 and 1, the joint destiny function satisfies the following inequality and equation. F of x is always more than 0, but their integral is equal to 1. The variables x and y are set to be independent random variables if their joint density function is the product of their individual density functions. At Sydney's restaurant, customers must wait an average of 15 minutes for a table. From the time they are seated until they have finished their meal requires an additional 40 minutes on average. What is the probability that a customer spends less than an hour and a half at the diner, assuming that for a table and completing the meal are independent events? Customers wait Customers wait an average of 15 minutes for a table. From the time they are seated until they have finished their meal requires an additional 40 minutes on average. What's the probability distribution? Is it uniform? Waiting times are mathematically modeled by exponential density functions, with m being an average waiting time. Okay, they should have said that in the question. X and y are random variables for waiting for a table and completing the meal, then the probability density functions are respectively. So for this, we have y. Clearly, the events are independent, and hence the joint density function is the product of individual functions. Okay, I will get that later. I will just read this chapter and then I will end this stream. I was doing some of the exercises took longer than I thought. When we define the double integral for a continuous function in rectangular coordinates, say g over a region R in the xy plane, we divided R into subrectangles with sides parallel to the coordinate axis. These sides have either constant x and or constant y values. In polar coordinates, the shape we work with is a polar rectangle, whose sides have a constant r value and or constant theta value, which means we can describe a polar rectangle as in figure 5.28 with r, the region r theta, r is between a and b, r is between a and b, theta is between alpha and beta. So r is between a and b and theta is between alpha and beta. And then we are dividing this into small regions. As before, we need to find the area delta A of a polar subrectangle, the polar volume of a thin box above Rij. Recall that in a circle of radius r, the length of S of an arc subtended by the central angle theta radians is S is equal to r theta. So theta is in radians. So this length over here, the arc length, is r theta. Notice that the polar region Rij looks like a trapezoid with parallel sides r theta and ri theta with the width delta r. Hence the area of the polar subrectangle Rij. So area is half delta r R delta theta plus Ri delta theta. Wait, so R theta gives the arc length. So arc length of the, okay, so arc length of the previous, so wait, arc length of the previous plus arc length of this times it by delta R. Okay, so when we look at it up close, it looks like a trapezoid. Look at this. So a trapezoid. Up close, it looks like this, right? But the area of a trapezoid, A, B, and then H, is this over 2. This plus this times the height over 2. This will look like this when this is very small. Simplifying and letting R star equals the average. We have the average times delta R times delta theta. However, the polar volume of a thin box above Rij is uh, so the F value times it by the area. Okay, so the delta area. So okay, so wait. It's this area times it by the height. That's the volume we are concerned for. Summarizing, we end up with, so the integral of this, by definition, it is this. And m and m go towards infinity. Evaluating a double integral over a polar rectangular region. So let's see. Um, CXDA over the region R, where R is theta radius, zero theta pi. But the thing is, it's defined by x, 3x. So in the xy plane, if we have this xy, then we have r, then r cos theta gives x, sorry, gives y, r sine theta gives x, and then tan theta opposite over adjacent. But this question is the equivalent of, so the region R, so between 1 and 2, and theta is between 0 and pi. Let me think about this. Wait, instead of writing x, I can write r, um, 3r sine theta d theta dr. Can we flip the integrals like we did before, the Fubini's theorem? So 0 pi 1 2. So we have times 2 is 6, and then 3 over 2. And let's write that as times 2 is 4 times 3, 12 over 2. You have 9 over 2. So 9 over 2 cos pi minus 1. 8 cos pi is cos pi is negative 1, right? So we are left with negative 9. Hold on. From 1 to 2 to 0 to pi. 3r cos pi r. From the figure, we see that we have 3r cos pi r. So why didn't this work? Why didn't r sin x, putting that here, work? R cos theta r. Wait, hold on. This is the y. I got it all wrong. Don't know why I did that. This is cos. This is sine. Opposite over adjacent. So we have r sine theta. Wait, I'm still right. R sine theta. Hold on, no. Why am I getting confused? The height, the height is given by the cos. This is sine theta. This is cos theta. Cos is the current x value. I don't know why I was getting confused. Sine gives the y value. So y over x. So this here is not sine, is cos. But okay, that I understand. But why the r at the end? Cos. cos, and then minus, I will take it outside, minus sine. So the thing is, why r over here? 3 r cos theta r. Okay, if someone can explain me this, great. Like after the stream, I will look at the comments. 'To evaluate the double integral of a continuous function by iterated integrals over general polar regions, we consider two types of regions analogous to type 1 and type 2 as discussed for rectangular coordinates, double integrals over general regions. It is more common to write popular equations as r is equal to f theta and theta is equal to fr. So we describe a general polar regions as t is equal to r theta. See the following graph. Double integrals over general polar regions if f of r theta is continuous over a general polar region as described above, then we have this. We have r as a function. Hold on. We have this dA and we have r at the end. Okay, no, wait, they added the r at the end. That's where the r came from. So if I want to change dA to dr theta, dr d theta, I have to add r at the end. How did I miss that? So then this becomes square, square, and then this will become cubed, which will cancel out the 3. 8 minus 1. And we are left with 9, positive 9. From 0 to pi, this is 0. Evaluating the integral, evaluate the integral. So we have sine of, hold on, what is this? Where D is a region bounded by the polar axis and the upper half of the quadrate R is equal to 1 plus cos theta. I don't understand what this is. It's sine of sine theta. As in the rectangular coordinates, if a solid S is bounded by the surface C is equal to f of r theta as well as by the surface r is equal to a, r is equal to b, and theta is equal to alpha and theta is equal to beta, we can find the volume V of S by double integration as this. If the base of the solid can be described as d, then the double integral for the volume becomes uh, we illustrate this idea with some examples. Find the volume of a solid that lies under the paraboloid z is equal to 1 minus x square minus y square and above the unit circle on the z on the xy plane. Okay, using a double integral. But don't we have to use the previous example? Like, where do we have to use polar coordinates? Why is this in the chapter of polar coordinates? Like, couldn't this be done by the previous method we learned in the last chapter? Notice the next example that the integration is not always easy with polar coordinates. Complexity of integration depends on the function and also on the region over which we need to perform the integration. If the region has a more natural expression in polar coordinates, or if S has a simpler antiderivative in polar coordinates, then the change in polar coordinates is appropriate. Otherwise, use rectangular coordinates. Square y square. So this they want to show is really complex in the using polar coordinates. As you can see, this integral is very complicated, so we can instead evaluate this double integral in rectangular regions as this. Finding a volume using a double integral. As with rectangular coordinates, we can also use polar coordinates to find areas of certain regions using a double integral. As before, we need to understand the region whose area we want to compute. Sketching a graph and identifying the region can be helpful to realize the limit of integration. Generally, the area formula in double integration will look like this. This is what we okay. Find finding an area using the double integral and polar coordinates. Evaluate the area bounded by the curve r is equal to cos 4 theta. Wait, uh, Desmos 3D graph. But there's one thing I don't understand. So the volume is this, the area 1 times R. So wait, let me plot this. Hold on. How do I do it in Polar? Right here. So the radius is 0. So R is equal to cos 4 theta. So what's the alpha and beta values then? Is it from bounded by the curve? Is it from 0 to 2 pi? 0 to 2 pi and example 5.33. We have 0, 2 pi and cos 4. But this is it's the same equation. The radius is cos varies from okay, so they use symmetry from 0 to cos 4 pi. Here the curve is bounded by cos 4 pi. R is equal to 0 all the way till okay. Cos 4 theta. Cos 4 pi. Oh, what is this? Hold on. Trig. I'm just searching up trig identities online of cos square. Open image. Like there's this formula over here. We have 1 plus cos 2 theta over 2. 1 plus cos 8 theta over 2, but this time it will become 4. 1 plus cos 8 theta over 4. Derivative of sine is cos sine 8 theta. But it's sine 8 theta over 8, right? Derivative of sine 8 theta is sine 8 theta over 8. Oh, wait. Derivative of sine 8 theta is cos 8 theta times it by 8. Is oh, okay. 2 pi plus sine 16 pi over 8. Is this on the right track? They got pi over 2. What is sine 16 pi? Sine 16 pi 0. Yeah, then it's pi over 2. This times this. Okay, I think that's it for the learning aspect, but I have to do the exercises because I'm pretty weak. I've forgotten a lot of stuff. I'm going to practice this, and then next stream I will start with the next bit that is about triple integrals. Right, I will end the stream here, and yeah, I'll see you guys next time. I will be learning basic physics next stream. I have a plan to learn basic physics next stream, and I hope I do that. Otherwise, see you guys next time. Bye.